Hello and welcome back to hands-on problem solving with machine learning. We're in a new chapter, linear regression, and how we can predict some median living costs in a dataset. So first, let us understand what is linear regression. Let's take a look. So I'm back in my Jupyter notebook, and I'm now in chapter 3, which is a slightly different notebook. So in this section, we want to deep dive into what is linear regression and how we can use it to do some housing price analysis with example data sets. So I'm sure all of you have toyed with linear regression as a model, whether it is from scikit-learn or some other machine learning Python library. But a lot of people tell me about their confusion on how linear regression actually works and how they can understand it in a way that allows them to debug the models correctly. So today I'm going to show you an implementation of linear regression. So this is not the only implementation you ever see. This implementation uses gradient descent to optimize the model, which is also one of many optimizations you can do. But this gives us a simple enough framework to understand how linear regression works. And with that understanding, we can do a better job of building linear regression models. So this example is spread between in4 and in5. We have two functions, one to train the model, which is in fit, and one to predict using the fitted model, right? We have three hyperparameters, which is the learning rate, which is how fast we want the gradient descent to work, whether we have an intercept in our linear model, which is currently set to true, and what are the weights, right? So let's first look at how we train a linear model. So we first want to take in the fit function, x, which is the example or the training inputs, and y, which is the example labels or the training outputs, right? So with global weights, which is a way for us to access the weights and modify them in the fit function, so we can use it later in the prediction step, we call global weights, which declares weights as a global variable. The next thing we look at is whether we need to fit an intercept. So here we have if fit intercept, which we know is true, and if we do need to fit an intercept, something quite interesting happens. So we call the NumPy concatenate call, which allows us to concatenate two matrices, right? So the first matrix is x, which is our training inputs, okay? And then the second one is a column of ones, which then, when combined with the coefficients or the weights on this column, gives us the intercept for each row in X, right? So we need to create a column of ones where the shape of these ones are firstly the number of rows present in X, which is accessed by x.shape, and the first elements of x.shape. And then the second one is we just need one column of the ones, so we feed in a 1 on the second shape parameter. This guy. And we want to concatenate them on a columnar basis, right? So we want the column of ones to be concatenated sort of row-wise or column-wise, depending on how you see it. But basically, all the rows in the ones vector needs to match up with all the rows in X, okay? So each of the 1 would then act as the intercepts. We then need to prepare the weights. The weights global variable is now initialized to the number of zeros that it takes to describe the number of columns that X has. So notice that if X doesn't have an intercept, then it will have one fewer column, thus needing one fewer weight than if it has an intercept. So here in NP zeros, we basically feed in the number of columns present in X, and then we use it to initialize the weights vector. In the next step, we're going to do gradient descents. Again, notice that apart from gradient descent, there are other optimization methods. In fact, there's an analytical solution to linear regression. But this is simpler for us to optimize, to visualize and get an intuition on how linear regression actually works. So for any gradient descent optimization, we need to specify the number of epochs that we train the gradient descents on. So here we are creating 1,000 epochs by calling range 1,000. So that guy there. Gradient descent essentially boils down to 3 steps. In the first line, we compute the current prediction by multiplying, or the dot product, so we're computing the dot product of x, which is the input, and the weights. A dot product really just means we're multiplying each corresponding column between x and the weights and adding them together. With this current prediction, we can see how wrong we are. So our error is our current prediction minus y, which is the perfect answer. And then we look at this gradient by computing the dot product of the transpose of our inputs with the loss that we're making and dividing them by the size of the perfect answer, which is stored in y. We store this value in gradient. To complete the final learning step, we multiply the learning rate by the gradient and we take it away from the weights. In this case, we can then use this gradient to understand how wrong we are and how to change the weights to offset our errors. And so in this learning step here, we modify the weights by the learning rate multiplied by the gradient. So after 1,000 epochs, what happens is the weights will stabilize and hopefully generate current predictions that are very close to y, which is a perfect answer. So once we have the weights, how do we predict things using a linear model? In in5, we have the predict function, which only accepts a matrix that has inputs. The predict function is going to use the linear model to predict each row that's contained in x. So the first thing we need to do again is to declare the global variable weights so that we get the weights in from the global namespace. And then again, if we're fitting an intercept, we need to concatenate a column of ones with the number of rows of x dictating how many ones in that column, and then combining them or concatenating them along the first axis, which is the columns. To find the predicted probability or the predicted value of the linear model, we simply need to compute the dot product of x, which is the inputs, and the weights. And that again is just putting a weight against each column in x, adding them together and calling that the result. So that is how the nitty-gritty of a linear model would function.